We can describe solution concentrations qualitatively or quantitatively. Qualitative descriptions are words like dilute and concentrated. Those are relative. So a dilute solution has a relatively small amount of solute compared to how much solvent there is. And a concentrated solution is going to have large quantities of solute relative to the amount of solvent. So these are of limited usefulness. We can have, concentrated or dilute. If you think about making concentrated orange juice into orange juice that you could actually drink, the stuff in the can is concentrated. There's more sugar and vitamin C and stuff in there for the given amount of solvent than when you put it into a pitcher and you add 3 more cans of water to it. Then it is dilute. So those are relative. Then there's lots of different quantitative measures. So here's a table summarizing some of them. We've talked about molarity. Other ones are molality, which I personally don't like, mole fraction, mole percent, parts by mass. That can include percent by mass, parts per million, parts per billion. You can also do parts by volume. Why do we have so many different solution concentrations? They are useful for different situations. That's why we have so many. So molarity. We covered this back in section 4. Let's review. So the molarity is the amount of solute measured in moles divided by the volume of the entire solution measured in liters. Always moles per liter. Molarity changes slightly with temperature because as you heat up a solution, the volume gets larger. If the volume of the solution increases and the moles don't change, then the molarity has changed. This usually isn't a problem for chemists, but it is a problem for some other people. So here's a brief review of how do you make a solution. You would weigh out, like if you're making, this would be making a 1 molar solution of sodium chloride. So 1 mole of sodium chloride in 1 liter of solution. You weigh out 1 mole of sodium chloride. You use the molar mass to find the mass that you need, 58.44 grams. You put it into a volumetric flask. You're going to add water and dissolve the solid and then continue to add water until you reach the mark on the neck, which specifies 1 liter of solution. Notice we didn't add 1 liter of water. The whole volume of the solution is 1 liter. And then you would have to mix it thoroughly, and then you've got a 1 molar sodium chloride solution. Any questions? Molality. So molality gets around the temperature dependence of molarity. Here we're looking at the amount of solute in moles again, but now we're looking at mass of solvent in kilograms. Instead of volume of solution in liters, mass of solvent. The mass of the solvent does not change with temperature, and so this is independent of temperature. Parts by mass and parts by volume are similar to each other. Parts by mass is the ratio of the mass of the solute to the mass of the solution, and then you're going to multiply by a factor. So percent by mass would be mass of solute divided by mass of solution times 100. Percent is per 100, so you multiply by 100 to get the percent. The units that you use for the masses here could be anything that's convenient for you. It's just important that the mass of the solute and the mass of the solution be measured in the same unit. You could measure them in pounds. 1 pound of solution, solute in 2 pounds of solution. The units cancel out, they go away, it doesn't matter. That would be a 50% by mass solution. And as we learned earlier with percentages, those can be useful as conversion factors. So if we say that a solution is 14% by mass, that means it has 14 grams of solute per 100 grams of solution. It's how many parts per 100 parts. Did I get the volume? Oh yeah, we'll get to that. So parts per million and parts per billion. We like to have numbers, quantities that are reasonably sized. So, like 50% is a nice number. 1% is a nice number. 1 times 10 to the minus 4% is difficult to deal with. And so we have different unit sizes so that we can use a unit that is convenient. So parts per 100% doesn't always work. If it's lower than that, we'll use parts per million. It's abbreviated ppm. Here you've got the mass of the solute divided by the mass of the solution. The difference is you're multiplying by a million. Parts per billion, ppb, mass of solute divided by mass of solution, times a billion. You could have parts per trillion. You'd multiply by a trillion. Okay? These can be used as conversion factors also. 15 parts per billion means 15 parts, here we're using grams, 15 grams of solute per billion, 10 to the 9th, grams of solution. For volume, parts by volume is the same, except we're looking at volumes instead of masses. So instead of the mass of the solute, we're looking at the volume. And we're looking at the volume of the solution. Again, you multiply by some multiplication factor. So you can have percent, which is parts per 100, parts per billion, parts per million, any of those. It's just volumes. So if we see 22% ethanol by volume, that's 22 milliliters of ethanol per 100 milliliters of solution. You could use any volume unit you want as long as you use the same unit. You could use liters for both. You could use gallons. Doesn't matter. Okay? Any questions? So we can have problems like this. What mass of sucrose, and they give us the formula here, in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? It says assume a density of 1.04 grams per milliliter. So to do a problem like this, we need to understand what a percent by mass concentration means. So 11.5% sucrose. Percent means parts per 100 parts. And this is by mass. So that means we have 11.5 parts of sucrose. What would be a nice mass unit to use? Grams. So 11.5 grams of sucrose. Percent is parts per 100 parts. So per 100 grams of solution. Everybody okay with that? There are other ways to use the percentage, but if you're good at those other ways, you don't need me to tell you how to do it. So for those of you that struggle with it, I would recommend this method. So that's what 11.5% means. What else do they give us? They give us the density. So the density is 1.04 grams per milliliter. Well, we've got two things here, right? We've got sucrose, and then we've got the whole solution, the soda. What's this the density of? The soft drink, right? So that's going to be grams of solution per milliliter of solution. Everybody okay with that? What's the other number they give us? 355 milliliters. The 12 ounces there is just for a point of reference because we're familiar with what 12 ounces looks like. And 355 milliliters is like, I don't know how much that is. It's a can of soda. Okay, so we wrote down the numbers, and what are they asking for? Grams of sucrose. So we've got milliliters of what? Is that milliliters of sucrose? Of solution. So we have milliliters of solution. And we want to end up with grams of sucrose. Comes down to unit conversions, dimensional analysis. So these two things look like they would be great conversion factors, right? Well, I've got milliliters of solution, and this uses milliliters of solution. So what if I put this in here? Stick that in there. That's milliliters of solution in the denominator and grams of solution in the numerator. SOL'(N) is what chemists do when they get tired of writing the word solution. So milliliters of solution cancel out. Now I've got grams of solution. I'm getting closer. I got the right unit. Would this help? Yeah, because this has the unit I want on top and the unit I want to get rid of on the bottom. So if I've got 100 grams of solution in the bottom and 11.5 grams of sucrose on the top, the grams of solution cancel out, and I'm left with grams of sucrose. So then I just have to do some multiplying and dividing. 355 times 1.04 times 11.5 divided by 100 equals. I don't have enough room there. How many significant figures should this answer have? 3. This 100 is a defined quantity. Percent is parts per 100, per exactly 100 parts. And so the significant figures come from the 11.5. 3 sig figs, 3 sig figs, 3 sig figs. So we'll go with 3 sig figs. And this is 42.5 grams of sucrose. That's a lot of sugar, huh? Any questions? So mole fraction and mole percent. Mole fraction is given the symbol chi, that's a Greek letter. Mole fraction is the amount of solute in moles divided by the total amount of solute and solvent, also in moles. It's measuring this in terms of moles, and it's asking what fraction of the solution is solute. This is the same as percent, except we haven't multiplied by 100 yet. So mole percent is the mole fraction times 100. So another way to express this is the mole fraction is the moles of solute, N, over the moles of solute plus the moles of solvent. It's the part over the whole. How many moles of solute divided by total number of moles? Okay, and then we just have this one example here. So a solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So we get a lot of practice in one problem here. Okay, well, let's start at the top. What is molarity? Moles per liter. It's moles of solute, and the solute here is the C12H22O11 divided by liters of solution. So do we know either of those numbers? We kind of know the volume, right? We're given the volume in milliliters, so we could move that into liters pretty quickly. That's 0.355 liters. How are we going to find the moles of sucrose? We need the molar mass. We've got the grams, we need the molar mass. So I'm going to get rid of this title up here because I want some space. So 50.4 grams of sucrose, C12, H22O11. We're going to use the molar mass, moles on top and grams on the bottom. So the molar mass will be 12 times 12.01, that's the mass of 1 mole of carbon, plus 22 times the mass of hydrogen, 1.008, plus 11 times the mass of oxygen, which is 16, and I get 342.3. 342.3 grams per 1 mole of sucrose. So 50.4 divided by 342.3 equals 0.147. This has 3 significant figures. This has 4. So my answer should have 3, but this is not a final answer, so I'm going to carry 2 extra digits to avoid rounding. So it's that many moles of sucrose. Everybody okay with that? So now that I have my moles, I can put that into this molarity equation. I've got 0.14724 moles divided by the volume in liters. So divided by 0.355 equals. This is a final answer, so we're going to round this to 3 sig figs. 0.415 moles per liter, or 0.415 capital M. Any questions? That shouldn't be too hard. We've done things like that before. Okay, mole fraction. Mole fraction is going to be what? Moles of solute over total moles. So it's going to be the moles of sucrose divided by the total moles. There's 2 things in the solution. There's water and there's sucrose. So we need the moles added together. So it's the moles of the solute plus the moles of the solvent, which is H2O. Okay? Well, this is convenient. We've already calculated the moles of sucrose. So we can plug that in. 0.14724 moles. And then in the denominator, we've got that number again, plus the moles of water. They didn't give us the moles of water. They gave us kilograms of water. Well, I'm going to convert kilograms to grams by multiplying by 1,000, 332 grams. And then that's H2O. And then I'm going to need the molar mass of water. So 1 mole of water to 18.02 grams. So 332 divided by 18.02 equals 18.4, and again, carry 2 extra digits, moles of water. That's a lot bigger than the moles of sugar. Is that okay? Yeah. We had a lot more grams of it, for one thing. So I'm going to plug that in here. 18.424 moles of water. Now, you need to be careful when you do this on your calculator. So I've got 0.14724 divided by, use parentheses, open the parentheses, 0.14724 plus 18.424, close the parentheses, enter. I'm getting 0.00793. And that should also have 3 sig figs.
Would there be a unit on it or not?
That's a good question. I was just thinking of whether to ask that or not. Is there a unit? No. Because here we've got moles and moles. Those add up, mole plus mole is moles. And we've got moles in the numerator. So there's no unit here. So 0.00793. The mole fraction should never be more than 1. If the mole fraction is 1, that means you have a pure substance, because the denominator is equal to the numerator. If you have a solution, the denominator is always going to be larger. Let's skip C and go to D, because that's just so easy from where we are. What's the mole percent? It's the mole fraction times 100. So that's going to be 0.00793 times 100%, which equals 0.793%. Question? Oh, just stretching, okay. A mole percent should never be more than 100%. You can't have a class of kindergartners and say, well, 120% of them are male. It's like saying out of 100 people, 120 of them are anything. Well, there aren't even that many people. It doesn't work, right? What should we do next? Percent by mass or molality? Percent by mass? We're skipping around, so let's just leave that skipped and we'll come back to him. So percent by mass, what does that equal? The mass of the solute, here we've been using grams, so let's keep using grams. So grams of sugar divided by the mass of what? The solution. So divided by the grams of solution times 100. Well, what's the mass of sucrose? 50.4. Cool, they gave that to us. What's the mass of the solution? We have to add the mass of water and the mass of sucrose. So here we've got the mass of sucrose in grams, the mass of water in kilograms. We did the conversion up here. So this is going to, in the denominator, it's going to be 50.4 grams plus 332 grams times 100%. I can pretty much guarantee you that on the test covering this chapter, there will be a question that asks you to find percent by mass, and I'll give you mass of solution, I might give you mass of solution, or I might give you the mass of the solute and the mass of the solvent, and a significant number of you will just divide by the mass of the solvent and get the answer wrong. So you've been warned. You have to add them together. It's the mass of the whole solution. So on the calculator, 50.4 divided by, again, I want to use parentheses because I want to divide by that whole quantity down there. 50.4 plus 332, close the parentheses, multiply by 100, you get 13.2%. Any questions? Notice that the mole percent and the percent by mass are very different. And that's because the molar mass of these two things is very different. We have less sugar than water, But the sugar has a much higher mass. And so when we do a mass percent, we get a much higher percentage than when we're just comparing the moles. And then we've got molality. Here's another warning for the exam 5. Some students see the word molality on the test and think it's a typo and that I meant molarity. No, the L was there intentionally. It's molality. So you're warned. Molality is what? Moles of solute, here the sugar, divided by, not grams, kilograms of solvent, which is water. It's moles per kilogram. So we do have those numbers. Here we've got the moles of the sugar, 0.14724 moles, divided by the mass of water in kilograms, 0.332 kilograms. So 0.14724 divided by 0.332 equals 0.443 moles per kilogram, or 0.443. I hate this. So the abbreviation for molality is an italic lowercase m. There's so many m's, right? It's not a meter. And you'd pronounce that molal, so 0.443 molal solution. I did not make this stuff up. Any questions? Oh, there's one more. Dang it. Okay, we'll do it. We're going to do it. We'll just grit our teeth and do it. What's the molarity of a 10.5% by mass solution of sucrose? There are so many different concentration problems that I could throw at you. You can't just memorize how to do each of them. You have to be able to understand the units. So I would approach this problem by thinking, okay, what's the molarity? Okay, well, what does molarity mean? So I'll write that out. Molarity equals, here we've got glucose in water. So it's the moles of glucose, C6H12O6, divided by the liters of solution. Knowing that tells me what I need to look for. I need to find the moles of sucrose in here, and I need to find the liters of solution. So then I'm going to go and look at the numbers that I've been given and see what those mean. I've got 10.5% by mass glucose. So that means there are 10.5 grams of glucose per how many? 100 grams of what? Solution. Well, that might be useful. And then I'm given a density, 1.03 grams per milliliter. Grams of what per milliliter of what? Solution. Grams of solution per milliliter of solution. So I need moles and I need liters of solution. We could take 10.5 grams of sucrose and calculate moles. I don't know how that ended up looking like a 4. It's a 6. One of the things that's disturbing about this problem is they don't give you an amount. They don't have to give us an amount. because the molarity is the same no matter how much of the solution you have. The percent by mass is also the same, whether you have a liter or a million liters. So what we can do is we can just choose an amount to make things easier. There's other ways to do it, but this seems to work better for most students. So let's say we choose 100 grams, right? We're just going to say, well, we're going to look at a 100-gram sample. How many grams of glucose are in 100 grams? 10.5. So to get the moles, we just need to take 10.5 grams and convert it to moles. So 10.5 grams of glucose. C6H12O6. Oops, not equals. Times. So we need a molar mass. Thank you. Somebody wants to get out of here. 180.156?
180.156.
156. Thank you. So grams per mole of glucose. C6H12O6. But you could just come up here and do this for me. No? Yeah. I am getting paid to do it, that's true. So I get moles here, 0.058. This is 2 sig figs. I'm sorry, 3 sig figs. I was underlining the 2 when I said that. 8283. Keep 2 extras to avoid rounding. So there's my moles for my numerator. I'm getting lost. 0.058283 moles. In the denominator, I want liters of solution. Remember, I chose, we decided to choose 100 grams to work with, 100 grams of solution. What's the volume in liters of 100 grams of this sugar solution? You have to use the density. So 100 grams of solution, and I'm going to put the density in here so the units work out. So I want grams in the denominator and milliliters in the numerator, and it's 1.03 grams. So that's going to give me volume in milliliters, but I want liters. So another conversion factor, milliliters on the bottom, liters on the top. Milli means 10 to the minus 3. I've got milli in the denominator. I put what it means on the other side of the line. 10 to the minus 3. So 1 milliliter is 1 times 10 to the minus 3 liters. And the milliliters have canceled out. So 100 divided by 1.03 times 1 EE minus 3. 0.097087 liters. This 100 is exact because it came from a percentage. The density is not exact, so 3 sig figs. Zero 0.097087 liters. 0.058283 divided by 0.097087 equals 0.600 moles per liter, or 0.600 capital M. Any questions?